Hi, folks. Today we're going to talk about foreign functions. That's when we have code in one language and code in another language, and a function from one language calls a function from another language. And sometimes they go back and forth, right? That's a foreign function call. That's what we're going to talk about. Specifically, we're going to talk about Rust and C and how they talk to each other. I like talking about Rust topics, and it turns out that for various historical reasons, talking to C is a thing that every language needs to do. Sometimes Python calls C functions. Sometimes Java calls C functions. Go calls C functions. Pretty much every language calls C functions. And Rust also calls C functions. So that's what we're going to talk about today. And on the one hand, this is a somewhat advanced topic. I want to admit, it's Rust and C are both kind of not the most beginner-friendly programming languages. And we need to know at least a little bit of both of them. If you don't know any C, that's okay. I think the first couple examples we do will be pretty easy to fake it, but stick around. But, Rust and C are both a little bit advanced as far as programming languages go, and the tools that we use to mix them together are pretty advanced. So it's a somewhat advanced topic. But on the other hand, I think it's pretty common for beginners coming to Rust for the first time to run straight into this topic. One of the things that Rust is good at is sort of mixing it in with existing code bases, often in C++ or in C. And if you do that, and that's maybe the first time you're learning Rust, the very first thing you have to do is learn how to make foreign function calls. So it's both an advanced topic and a topic that beginners tend to run into pretty early, at least depending on what company you work for or what your projects are. So I think it's sort of worth teaching the topic from that sort of compromise. It's like, it is advanced, but as beginners, we often need to do it. So that's what we're going to talk about today. And then another funny little thing about foreign functions, especially foreign functions in C, is that we often call them without even thinking about it all the time. So it turns out, for example, that even printing ends up calling a C function. If we drill down and down and down and down and down into the details, we see that calls a C function. So actually the very first thing we're going to do is look at that and think about how we call foreign functions all the time without even knowing it. And then from there, we'll go into a slightly more complicated example where we have our own C code on the other side, not just the standard library of C functions. And then from there, we'll go into a slightly more complicated and interesting example. So that'll be kind of how we pace ourselves here. So let's start by looking at printing. So I have a very short Rust program here. And in fact, I also have it up in my terminal. And I'm going to do this in my terminal. But the slides you see here, I will link to these in the description of this video. I'll also link to the repository that has all the code examples that we use here. You can run these yourself. So I'll pull up the same thing in my terminal. This is that program, and we can run it and see that it prints hello world. So of course, most of the time we would use println with println exclamation point, right? It's the standard way to print things in Rust. And if you look at the definition of println, there's a lot of complicated moving parts. And there's also a couple of slightly more complicated helper functions on the Rust standard library write trait. Technically, those are in the picture here, and we're just going to skip them. I'm going to go straight to standard out write. So as you just saw, this is code that you can run. You get an object from the standard library called standard out, and you can call write on it. Technically, it's more correct to call write all. We're not going to worry about that. So we can call write on it, and that writes the bytes out. So this is basically this sort of the simplest way to do directly what println is doing for us most of the time. So we are writing bytes directly to standard output. And I want to start us off by doing a little go to definition scavenger hunt to see what actually happens when we write to standard out. So let's do that. So I have Vim here, and it's hooked up with Rust Analyzer, but there are many ways to get go to definition working in Rust. You might use VS Code. Rust Analyzer is often the sort of the thing that makes go to definition work. And I go to definition like that. So I've gone to the definition of the write method, and now we're looking at standard library source code, which tends to be a little bit, busy, right? There's a lot going on, but, we're going to try not to look at too many unnecessary details. We're just going to try to drill down. So the first thing we see is that the write method on standard out just calls the write method on a reference to itself, which is kind of funny. I'll just go to definition immediately. Now we're on the implementation of the write trait for reference to standard out. Okay, kind of funny, but that's what it does. And that calls lock on itself and then calls write on that. Some of you may have seen that lock is actually a public method that you can call in the standard library. It turns out that, many threads can print at the same time. So there are locks involved, and sometimes we want to take those locks explicitly. But I'm not going to worry too much about the details. I'm just going to go to definition. So now we're looking at the implementation of the write trait for standard out lock, which again is a type that exists in the standard library. It's public. You can use it. It's got a lifetime. We're not going to talk about that at all. We're just going to look at the write method. Okay, we call inner, borrow, mute, write. I'm not going to ask too many questions. I'm just going to go to definition. And now I'm at something called a line writer. And I'm kind of doing this on purpose because I want to say that I just made a mistake, or maybe I just kind of went down a path that didn't end up being what I wanted. So, line writer is part of the story here, but what we see if we look carefully is that now we're in a type that is generic over writers. So instead of having anything in here be about standard output specifically and how it works, this line writer type can work with any writer. And so if we keep going to definition here, we're actually not going to find the code that we're looking for about how standard out works. So this happens sometimes when we're playing around in the standard library. So I'm going to go back. So we might guess that the standard output type is going to be somewhere in here. So I'm just going to take a guess, which I've done this already, so I know this is correct. I'm going to go to definition on inner. So here we see the standard out lock is this is a little bit noisy, a reentrant lock guard of a ref cell of a line writer of standard out raw. We saw a line writer. We kind of wound up there. This is a really kind of interesting tangent that we could go down about why a lock would have a ref cell inside of it. Turns out the mutable aliasing rule has something to do with that. You can get more than one reentrant lock guard at a time. Not going to worry about that little tangent because we can see, okay, standard out raw. That's probably what we want here. So I'm going to go to definition on that. So, okay, so standard out raw is just a thin wrapper around something called std.io standard out. Just keep doing a definition. Though I'll warn you in advance, as I go to definition here, watch down here, look at the file path that we're looking at and see it's going to change by quite a bit. So went to definition. Again, we're seeing a thin wrapper, in this case around nothing. It's kind of funny. But that was a big change. Let's go back and forth and see that difference. So we went from the IO, so standard source, this standard library source is IO module, standard IO file, submodule. We went from there to standard sources syspal Unix, right? So this is it's sort of a different corner of the standard library. PAL stands for platform abstraction layer, I think. And so now we're in sort of Unix specific code. So if we're on Mac OS or on Linux, this is the code that is working for us. But if we're on Windows, we would go to different files. So now we're really getting into the nitty gritty. We can see, okay, standard out. I'm just going to scroll down. We can see already, like, there's the read implementation for standard in. So we're probably pretty close. Scroll down. All right, yeah, impl write for standard out. Great. We see some other stuff that we could look at if we wanted to. Manually drop. It's a standard type in the standard library. We could look at all these things, but we're not going to. We see that there's a write method there. I'm going to go to definition. Now we're in fd.rs in the PAL. Okay. Now we're doing something with converting return types, and we see that we're calling a write function, not a method anymore, a function in something called libc. Libc turns out to be a Rust crate, a Rust library that supplies bindings to standard C functions, which is something we're about to learn how to do. And the Rust standard library uses libc internally. And we can go to definition again. I'm just going to, just ignoring all these details about how exactly we call the function. I'm just going to go to definition again. And there we are. And now there's some noise here, something specific about Mac OS and what the name of this function is. Who knows? But we can see, okay, there's our function right there, and it has no body. right? It's not no curly braces here. There's no code here. This is just a declaration. This is saying this is the shape of a function. This is its signature. It's defined somewhere, but not here. Turns out it's defined in the C standard library. So folks who are familiar with C are familiar with how C does header files, right? In header files, you have these declarations of functions, and the bodies are somewhere else, and the compiler and the linker figure it out, right? This turns out to be the same story. So we found ourselves at the declaration of a C function. This turns out to be how Rust does it. If I go up several hundred lines, let's see if I can do that in one keystroke. Yeah. So we went up 500 lines, and we see this is an extern C block. That's how Rust labels these things. So this is a C function, right? So we went from this call to it and then to its lack of a definition. So the next thing I want to do is do this ourselves. And we just saw that there was a lot of code and a lot of types and things in the standard library, but we don't have to do any of that. We're just going to do it the simplest, shortest possible way. In fact, I'm not even going to use write because write takes a file descriptor and a pointer. I just don't want to do it. I'm going to use a simpler function called putchar. So let's do something very simple, very similar ourselves using putchar. Putchar is a function in the C standard library that's even simpler than write. It doesn't take a pointer to bytes. It just takes one character and it prints it to standard out. So let's look at a very simple program that calls putchar. So here we can see that we're doing exactly the same thing as the libc code was doing. We have an unsafe extern C block. We're declaring a function. We could go look at the docs for putchar and kind of convince ourselves that these types are correct, but they're correct. cint is a type alias in the standard library. It's going to end up being an I32 on my platform, but it's different on different platforms. That's why it's there. And then whenever we call a C function, that's unsafe. So calling putchar is going to be in this unsafe block. And we're going to loop over all the characters we're going to print, and we're going to print them with putchar. So I should be able to see, yeah, here's the code. So here's the code of my terminal. We just looked at it. And I should be able to run this. Hello world. So I just made, 11, 12 calls to putchar. And those are C function calls. So this is the smallest example I could come up with of calling a real C function. If you wanted to do this in the real world, you probably wouldn't go through the trouble of writing this declaration out yourself, because as we saw, the libc crate provides it for you. So I go back to the slides, the next slide. How I would actually do this if I wanted to call putchar is I would use libc putchar, which is the same declaration. I just don't need to type it, and my program would get shorter. So libc is a dependency. That's what I would actually do. So this is a foreign function. It can be this easy. Of course, this is slightly cheating because this isn't our code, right? This is the C standard library, and there are some functions available, but there's actually a lot of functions available, but we don't get to put code in the C standard library. So whenever we want to call our code, we need to do a little bit more work. So the next example we're going to look at is the smallest example I could come up with of how to call our code in C. And the simplest thing I could think to do was adding numbers. I needed two functions. So we're going to add one and we're going to add two. So here's the three most important files in the second example we're going to look at. I'll pull it up in my terminal so we can convince ourselves that it actually runs. This is main.rs. I put that on the slide. Yeah. So this is main.rs here. So that's that in my terminal. And if I go in here and I say cargo run, we see that prints 42. Okay, and 42 is add 2 to 40. That makes sense. So, okay, this runs. What is it doing? So there's add 1 and add 2. We see that this add 2 here, yep, there's our unsafe extern C block. So that's just a declaration. And the real function we can see is over here in the C code. This file I've called add2.c. And add 1, okay, this is actual code, right? This function actually has a body. So this is a real Rust function. It's got some junk on top of it. We'll talk about that. And on the C side, there's a declaration, right? So the add one function we just said is defined in Rust. So in C, we declare it. We give it signature, but we don't define it. So you could imagine that this line here, it could be in a header file that might have gotten included, but it doesn't matter. Here we've just got it in the code. And I could have used int here and done the same cint thing that we did in the last example. I chose to do it differently here. So C does have these types that say exactly what size they are, and they're from this standard header. And so if you do it this way, then you can just use I32 on the Rust side, and I find that a little bit more convenient. You can do it either way. So okay, so just tracking the execution of the code. So main calls add2, and then it prints the integer that add2 returns. Add2 is a C function. The C function calls add1 twice. Maybe not the most efficient way to add 2 to a number, but this is fun. And so add2 is going to call the Rust add1 function twice. So that's what's happening here. You'll see that the C code, other than this type that I've chosen to use, doesn't really have any special annotations. This is just C. The Rust code does have special annotations. We'll talk about these real quick. No mangle refers to how the names of functions get written into the final binaries that we compile. So, of course, in Rust, it is possible to have more than one function called add1, right? For example, there could be multiple different crates that have an add1 function. There could be multiple different modules in the same crate that might have their own add1 functions. And when you get down to the binary, all those functions need to have unique names. Each function in the final binary needs to have a unique name. And so normally, the Rust compiler is going to take the name we gave the function and mix in a bunch of other stuff about what crate it's in or what module it's in, or the name ends up having a bunch of random numbers on the end of it. C does not do that. So the add2 function in C is going to literally be called add2 in the binary. And for that reason, you cannot have more than one function called add2 in C, at least not without some other annotations. So this no mangle magic directive here is telling the Rust compiler, don't do the normal thing where you add a bunch of random junk to the name of the function in the binary. No. Do it the C way. So this function will literally be called add1. And if there was another function in Rust or in C that tried to do the same thing, it would actually be a linker error, I believe. I have to try that. But so that's what that's about. And extern C is just saying that this function works the C way. And if you've written a lot of assembly, you may have seen what it's like to call functions from assembly. And there are rules, and the rules can be different depending on what language you're talking about and different flags you can pass in. And so this is just saying, no, the way you call this function is the standard C way. And that's good because we're going to be calling this function from C without telling the compiler anything magic about it. So the C compiler is going to call add1 the C way, and extern C is just telling it to be ready for that. That's what that means. Lots of details we could get into. We don't need to worry too much about it. And then, of course, the last thing we need to do, we have written this C code, and so we're going to invoke cargo to build our Rust code, but cargo does not automatically know how to build C code. And so when we do this, we need to build the C code in some way, and the common way to do it is to use build.rs. So build.rs is a standard file that cargo knows about. If I go to the terminal, you can see that typically build.rs is in the root directory of the project right next to cargo.toml. So I put the source files in the source directory, but build.rs is at the top. And cargo knows about that. We don't need to tell cargo about it. If it sees build.rs, it will compile it and it'll run it as part of your build. And it can do anything. I mean, it's just a main function. You can put anything in here, but what we're going to do with it is sort of the most common thing you might try to do with it. So in this case, what we're going to do is we're going to call the cc crate. So we could have written, for example, standard process command calls to sort of shell out to GCC or whatever compiler we wanted to use. We could do that. Then we would have to figure out the other side of the story, which is telling cargo how to include the compiled files that we generated. I don't want to have to know about any of that. And so if there's just one thing that you take away from this entire video, it should be CC crate. Like, use the CC crate. It is wonderful. So it will figure out how to compile our C code using some appropriate defaults for the platform. For example, this works on Windows, which is amazing. I'm on Linux here. This is a Linux VM actually for this video, but the CC crate works on all the major platforms, and we pass it the code file we want to build, and we give it a name. This name doesn't matter. You could put random letters here. That's fine. And it's going to automatically do the sort of shelling out to the compiler as appropriate. And it's going to do the other half of talking to Cargo. So we can see an example of that here. So it turns out that the way that build.rs talks to Cargo, what Cargo expects is that build.rs is going to print some stuff. So it prints things that start with cargo : and you can pull up the docs, and there's a lot of different commands it can print. So this is a relatively simple example. So this is saying, hey, if this C file changes, Cargo, you should rerun this build.rs. You should do all this stuff over again. So every time you run cargo build or cargo test, it's going to look at the modify time of this file. And if it sees that it's changed, it'll rerun all of build.rs. That's nice. You might have expected that CC would kind of do that automatically. It does seem like a nice thing to do by default. I think the reason they don't is because a lot of C projects, C libraries have header files, and you only pass the C files, not the .h files, to CC, and figuring out what all the .h files are gets a little thorny, especially if you think about all the different platforms, Windows, Linux, Mac, cross-compiling. It gets a little thorny, and so I think they just decided not to do it at all. So if we want this, nice default, if you change this file, rerun the build, we have to ask for that ourselves. But that's a good example of how build.rs gets to tell Cargo to do things. And I believe on the next slide, I have a nice command that's going to let us see a bunch of junk. So let's run this. So touch build.rs is just sort of pretending that we've modified it. Update the modify time. That's going to force a rebuild. And then I run cargo build with the verbose flags, and you can look up the CC docs to find this variable. I had to Google it. That's how you get CC to print lots of stuff. So I'll open a new terminal and we'll run that, and we can see lots and lots of stuff. So scroll up. This is all CC output. I think it's printing lines for each of the environment variables that it's reading, I think, because a lot of these are not set. And then you can see that it's printing some output every time it runs the compiler. So here it's saying, it ran CC, that's the sort of default standard alias for the system C compiler. And it compiled a file called something detect compiler family.c. So that's not my code, obviously. We didn't write that. That's sort of a hack in CC where it uses the compiler to figure out, what platform you're on and what sort of flags are supported and all these things. It does a lot of stuff that we don't want to have to know about. If we scroll down, we can see, okay, here I think is where it actually compiles my code. So it's invoking CC again, and there's add2.c. So this is the command that the CC crate is running for us that actually compiles the C code. And then we can see, if we scroll most of the way down, we can see the most important cargo sort of directive or command right here. So it's saying, hey, Cargo, I want you to link this binary file. I think in this case it starts out as a .o file, and there's another command that turns it into a .a file, and we don't have to know about any of this, right? This is all noise and just complicated details. Folks who are experts in C might be very interested to read this output and see exactly what flags everything is using. Go nuts. But most of us are just happy to let CC decide to do what it's going to do. This is these are commands that exist that Cargo knows about, where the build.rs can tell Cargo to link in the code that it compiled. That's it. We're not going to ask any more questions about that. That's a lot of code, or a lot of output. Anyway. And so, so that works. And we can see, let me go, we did say recompile this if I change the code. So I can go change the code, and I can change add 2 to add an extra 5. We'll put an extra 5 in there. And if I say cargo run instead of 42, I think I'm going to see 47, and I do. So this is actually compiling the C code. If I put a bunch of, nonsense in here, right? We should get a compiler error of some kind, right? There's a lot of output. Yeah. Okay. Right. Expected a semicolon. I guess that's how the C compiler reacts to that nonsense. Whatever. So this is compiling the code. We'll get rid of those changes. Cargo. Run. So cool. So that's add to. So that's just about the simplest example I can think of having Rust code call our own C code that's doing whatever we want. And actually, in this case, the C code's calling back into the Rust code, both directions. So we can put whatever code we want in here or in here, like I just did. So this is great. I mean, this is all you need for sort of hello world style examples or really simple examples. But when you start getting into real libraries, like, say you want to call a big complicated library, maybe something like OpenSSL or zlib. Of course, in real life, there are already Rust crates that have wrapped those things and you don't need to figure this out on your own. But, you might have a library in your company or whatever that has a lot of functions in it, maybe a lot of structs and other things. And having to write out all these bindings is, well, first of all, it's really annoying. It's a lot of typing and you have to keep converting the types back and forth. And that's frustrating. Maybe more importantly, there's a reason this is unsafe, right? And it's not just that C functions can do anything, or they can, right? C doesn't have a borrow checker. So C functions can certainly do bad things, but maybe the bigger problem right here is that if we got this type wrong, that alone might be enough to cause memory corruption or who knows what, right? We could swap the arguments around and then C would get confused and, we'd have to pull out the debugger and see what the heck happened, right? So writing these out by hand can be a lot of work if there's a lot of them, and it's very sensitive work, and we do have to be very careful not to get it wrong. So for the last example, we'll make it a little bit more interesting. We'll have a few more functions, and I'll introduce this other tool that we really like to use in these cases called Bindgen. We're gonna write a linked list in C, and we're gonna use Bindgen to help Rust talk to it. So I think, we'll get to that. Let's look at the C code first. So in this case, it's a little bit more complicated. So I've got a header file and a source file. So this is normal in C. The structs have to be defined in the headers. And then these are declarations of the functions that we will define in the C file. So this is implementing a linked list. This is probably the point in the video where folks who have not actually written any C are going to fall off the train. And that's okay. Feel free to just listen along and do your best if you like. Folks who have written a lot of C, many of us have written linked lists in C. This is a fairly common thing to do. It turns out to be somewhat more complicated in Rust, but it's not too complicated in C. So our linked list node has some data in it, some element, right? And in this case, I'm calling that a void star, right? C does not have generics. There are tricks you can do to avoid using a void star here, but we're just going to use a void star. So this is a pointer to some element that is of who knows what type. We're not going to ask. And that basically means that has to be allocated on the heap. Those of us who know the stack heap distinction in C and in Rust, this element is presumably allocated on the heap and our node is going to own it. And then each node has a pointer to the next node. And the idea will be that at the end of the list, this next pointer is going to be null. So the last node has a null next pointer, and every node presumably has a non-null element pointer. I guess you could put a null pointer here, but we're not going to do that. And we can push and pop the list. And again, folks who've written a lot of C have probably written this code a dozen times. But we can look at it real quick. It is kind of a funny C thing that in examples like this, we often have star. I do think this is a very interesting point of comparison to Rust. So this is a pointer to a node, and I'm calling it list. If we were to write a function like this in Rust, the list type would probably look like this, right? So a pointer to a node is, we're going to call it a box node. Of course, Rust has many different pointer types, but box is like the one that owns its contents, right? So a pointer to an object that owns that object would be a box. That's how Rust would say that. And of course, like we said, these node pointers can be null. And so if you have a box that might not be there, that's an option box. So this is kind of how Rust might have written this first layer of the pointer type here. And then the second layer of the pointer type, I'm going to call that a ref mute. It's another type of pointer in Rust. Again, this is C, so C doesn't distinguish any of this. But in Rust, we would say like, oh, okay, yeah, we're taking a pointer to this thing and we want to modify it, right? We don't want to take it away or copy it. We want to modify it in a way that the caller can see. And so that's typically a ref mute. And the other thing about ref mute is it cannot be null. And it's true that we would be surprised if this outer pointer was null, and we're going to end up writing some code that doesn't check it. The inner pointer can be null at the end of the list, but the outer one cannot. And Rust would make that quite explicit. If we were to type this out in Rust, it would probably look like this. But believe it or not, the sort of underlying memory layout, the underlying assembly generated for this type and for functions that manipulate this type would end up being the same as what C is doing here. This basically is a star. This is a pointer to a pointer. But we're in C, so we're going to type it out this way. And we can see, okay, so when we push onto the list, we malloc, right, heap allocate a new node. Remember that the element is presumably already heap allocated. So each node kind of involves two heap allocations, but the push function is responsible for one of them. We copy the element pointer in there, and we know in our heads that means that the node takes ownership of the element. C is not explicit about that. You just have to be careful. And then we point the new head's next pointer to the existing list, and then we reassign the existing list so it's pointing to the new head. So, typical linked list implementation. And we do the reverse on the pop side. On the pop side, we're going to return the element pointer. But if the list is empty, there is no node. In that case, we'll say that we return null in that case. And hopefully the caller doesn't put any nulls in the list. That would be a little confusing. We're not going to do that. Okay, so this is a linked list in C. And if you've never written anything like this before, you can squint at the details. It's not critical. So, right, as we said, instead of writing out the extern C blocks and trying to translate all these function signatures and actually this type, instead of doing either of those things by hand, we're going to use a tool called Bindgen. So that goes in the build.rs. We saw this called a CC and these print lines. This is similar to what we saw before. Nothing new there. This is all new. So we're going to call Bindgen. It has a builder type in its API. We pass it in the header that we are using. And again, I'm going to go back. That's this file, right? We give it this file. And we call generate. And then it turns out that what you're supposed to do with that is call write to file and write it to a temporary file. And conventionally, there's some junk with an environment variable. And the truth is that when I write this, I don't remember how to write it. So what we're going to do is I'm going to pop up my browser and we're going to say Bindgen docs. I probably should have opened this tab. I'm going to click the Bindgen user guide. And you would just look through here and you would say, okay, yeah, creating a build.rs file. And we would look at what they did and we would see, okay, yeah, create a builder, give it the header, call generate, call write to file. So, of course, I don't remember how to do any of this off the top of my head. I Google it. And you can see that I've slightly tweaked the error handling, for example, here. I've done this in a very slightly different way, but this is basically copied from the Bindgen docs. So you just go look at those docs whenever you need this. So this generates some Rust code, which we're calling bindings.rs. And then on the flip side, our main.rs, I think in this case, I'm going to do a lib.rs. We're going to make this a library crate. Our lib.rs needs to pull that in. And so that looks like this. And again, this is a bunch of junk. So now we're looking at the start of lib.rs. And there's a bunch of junk. And we see that environment variable again. And something, the include macro, which we don't use very often. This is kind of weird. I'm going to go right back to those docs. So going back to the Bindgen docs, we would click the next section, including the generated bindings. And we see like, yep. So basically the first time you do this, copy paste from the docs. You don't have to memorize this stuff. They like to include kind of directly in the top level file. I like to make a little module. I like to call it the FFI module, the foreign function interface module. You can do it either way. And then these directives are to suppress warnings. I think in this case, we actually would not get any warnings, but it's very common for C functions and C structs to have different naming conventions than Rust ones. Like you might have a struct with a bunch of underscores in the name, whereas a struct in Rust is typically supposed to be like snake case. That's what this is about. So the Rust compiler will often spit out a bunch of warnings when it sees these weird names, and we don't want that. Because we're just going to use the same names as C. That makes everything easier to understand. So this is how you tell the Rust compiler to stop generating all those warnings. This is not required, but it's common. And if you copy paste from the Bindgen docs, this is what you'll get. So again, that was a lot of kind of random junk. We called Bindgen in build.rs, and we included the resulting code in lib.rs, and I'm not going to squint too hard at exactly what it did. But it is very interesting to go look at the generated code. I have it on a slide here, and I think what I'll do is I'll just use my terminal again to pull that up. So I'll go to lib.rs, and yeah, you can see there's that include, and there's a bunch more code that we're about to start talking about. But I think the first thing I'm going to do is just go to definition on one of these things, and we see the same code. We should see the exact same code as my slide right there. Right. So what Bindgen has generated for us is a struct definition. And so we can look at these types and compare. Let me go back to the header, right? So there's a void star element and a node star next, right? The next pointer. And what Rust calls that is a star mute. So the basic star in C is a star mute raw pointer in Rust typically. And you see there's a C void type alias somewhere in the standard library, and Bindgen uses a slightly odd syntax that we don't usually type that leading : : but you can. It turns out that's standard Rust syntax. So, okay, Bindgen spits this out. What we can notice repr C, that's pretty similar to the extern C that we saw on our function declarations. In fact, we see it down here. It's extern C. In both cases, they're telling the Rust compiler, do things the C way, which is clearly what we want here because we're talking to C code. We don't have to get into the details of what exactly that means, but if you read the Rustonomicon or something like that, you'll learn all about struct layouts in memory and all these things. But anyway, it copies the struct definition, and then we get our declarations of the functions we needed. And again, it might have been a little fiddly to figure out that a node star is in Rust terms a star mute node, but that's what it is, and Bindgen just does the right thing, thank God. We see C void again, but otherwise this is a pretty direct translation of the C header file. There's some other junk in here. This turns out to be basically asserts. This is Bindgen kind of testing itself and making sure that its layouts are correct. And if you really stare at exactly what it's doing, the syntax is very funny, and I'm not going to worry about it. But it turns out this would generate a relatively easy to understand compiler error if Bindgen was surprised about the size of a type. I'm not going to worry about it. So, okay, so we've included this in lib.rs, and now we need to start using it. So usually what we want to do is, instead of exposing like raw pointers to the caller, to the rest of our application code, we want to wrap this in a nice, safe Rust type. Right? That's what Rust is good at. Right? Rust is good at wrapping safe abstractions around dangerous, unsafe code, or in this case, around C code. So this is how we might start to do it. In this case, the struct is just going to have a head pointer on the inside, and we remember, like, okay, when this is empty, we expect this to be null. And then when it's non-empty, this is going to be non-null. And the C push function is just going to mutate this for us. That's what we're going to do. And we can write a new function. And it turns out that we don't need any unsafe code, actually, to create an instance of this struct, because creating null raw pointers in Rust is safe. You're allowed to create as many of them as you want. You can't use them without unsafe code, but you can create them. So we don't need any unsafe code for new. Unfortunately, if you write it out just this way, you run into a compiler error. There is a compiler error here, and everybody hits it, and it looks like this. So it turns out there's a rule. There's a rule that says when you have a generic parameter, T, and by the way, we should go back and talk about that. So, of course, in C, we're using void star because the C compiler doesn't know what our types are going to be. We want to use different types in the list. We use a void star in C. In Rust, we're going to make that generic. We're actually going to have the compiler know what the types are, and we're going to have to figure out how to do the right thing. So we'll sort of see how that plays out. But here, the first thing that happens is we get this error, right? Unused type parameter. So the Rust compiler is looking at this type parameters list. Okay, you got to type T, and it's looking at the members, which is just a head, and it's seeing, you don't use T anywhere in the struct itself. And there are various reasons why the compiler really wants you to use T in the struct. It's not happy to just not worry about it. It turns out there are some rules to do with lifetimes and exactly how they work. There's some rules to do with the send and sync traits, if you've seen those. And I'm sure there's other rules that I don't know about. And the compiler wants to know how you're using T to get those rules right. And so for that reason, whenever we write code like this, you can see that there's a hint here. We need something called PhantomData. And it looks like this. And of all the details we've seen so far, this is the one that's really like, you just kind of have to ignore it at the beginning. When you go read the Rustonomicon, you can learn all about exactly why PhantomData is here. You can see that PhantomData just contains a T. In this case, this turns out to be the right way to do it. And when you create a PhantomData, you don't even give it any arguments. Like the PhantomData contains nothing. It's zero size. It's just there to kind of satisfy some fiddly rules in the Rust compiler. So when you do projects like this, you will forget this. You will write the type. The compiler will yell at you just like that. And you'll remember, you'll throw PhantomData in there and you'll forget about it. And it's fine. It's fine. But you will run into this. So this is a thing we have to do. Assuming we do that, again, luckily the compiler at least reminds us that we have to do it. Okay. Then the next thing we want to do is actually call those functions, right? We want to call push and pop. So we need to define wrappers for those. So you can see the push method and linked list push is going to call the FFI C function right there, and linked list pop is going to call where did I do it? FFI linked list pop. So let's look at how I do these. So the call itself is not too bad. We've seen that before, right? We did that with add2 and with putchar. So calling the function is no big deal. It turns out that our biggest concern here when we write the push method is this guy, right? So we're going to have T. I think we can see, I have some examples here in the terminal. You see I have some tests at the bottom of lib.rs. And in this case, I'm using an integer that's going to default to be i32. So, we could imagine that T might be i32, but T could be anything. T could be a string. T could be a file. Who knows? T could be a reference. It turns out some of those complicated rules have to do with when T is a reference. I'm not going to worry about that. T is anything. We don't know what T is. But if T is an int, the C API wants a pointer to int. And we need that pointer to own its contents, which is not what, raw pointers necessarily do in Rust. They can go either way. So the way we're going to make that work is box, right? So box is the way that Rust puts an object on the heap. If you've heard of the heap, it's not critical, but it puts it behind a pointer, and then we treat that pointer like it owns the object, and it does. So we say box new, and whatever type this is, let's think of it as i32. Whatever type this is, we put it in a box. So we allocate space for it on the heap, and the box is a pointer to that space. Now, the next problem is that because the box owns that memory allocation, its job is normally to free that memory allocation when it goes out of scope, right? So the element box variable goes out of scope at the end of the function, just like any other variable, and it would free that memory. And that would be very bad because, of course, we're going to give a pointer to that to the list, right? And the linked list push is going to put that in a node, and that's going to be in our list. And the list basically expects to own that object. That's what we expect it to do. And so if we freed that memory at the end of push, then we would have this garbage dangling pointer in our linked list. I mean, we need to not do that. It turns out that the into raw method takes care of that for us. So if we wanted to, we could go look at the docs for box. I'm not going to pull them up, but the into raw method consumes the box by value, and it promises that it never frees that memory. So into raw gives us a raw pointer, which is specifically a star mute T. And we're going to cast that into a star mute C void, which is what C wants. C doesn't even want to know about the type. And all pointers are the same size, we can believe. And so So we're going to cast away the type. We're going to remember what it is because the Rust type system at compile time will remember what it is, basically. There will be no runtime type information here, but we will remember, and the Rust type system will kind of keep us safe. So into-raw has promised that it has consumed the box by value, and it's promised not to free the memory. We could go read the docs. That's what it does. Okay, and then we make the function call. The last interesting detail here, I have a note about it. So self.head, if I go back, we can remember, let's look at it here, right? Like self.head is a star mute FFI node, star mute node, a node star. But if we go back to the C function, the C function wants a node star, right? A star mute node, right? It's modifying our node, right? It's going to repoint our head as it pushes. So what we've given it is not a star mute node, but a ref mute star mute node. Is a little different, is that we've given it this, basically. But it turns out that the Rust is happy to automatically convert this into that. This turns out to be a relatively common thing to do when you're talking to C code. So that conversion is automatic. It's called a coercion. So that just works. We don't have to worry about it. And we could just type that. We could do a cast with the as keyword if we really wanted to, but Rust does not make us do that. But we could do this same cast, but we don't have to. Okay, so that's push. Pop just does the opposite, right? So we call our pop function, we get that void star, and then we said that void star can be null, right? So if the head pointer is null, if the list is empty, we expect a null here, so we check for that. And that means that we're returning option T. We might return a T. We might not return a T. If the list is empty, we don't return a T. That's return none. But if it was non-null, we use box from raw. So that's sort of the counterpart, the opposite of into raw. Makes sense? So that takes a pointer. Almost always, this is going to be a pointer that used to be a box. That's what it is in this case, right? We created a box and we called into raw. You can do other things and create a box from something that was never a box. We're not going to worry about that. That gets into some complicated questions about the global allocator that we don't care about. But luckily, we know that this pointer came from into raw. So we call from raw. We get the box back. So at that point, lmbox is a box T. And we did an as cast to get the type information back from that void star. Because, of course, the pop method knows that it's a method on a linked list T. So it still has T in a sense that only really applies at compile time. It still knows what T is statically. And so it can do this cast back, and then everything else can sort of provide the right type. There's another little funny detail here. So the way, of course, pop, we don't want to return box T. The boxing is just an internal implementation detail. We want to return T. So we need to get it out of the box. It turns out that the way that you do that in Rust, you could read the box docs. This is the standard safe thing to do with the box, is dereference it. We star it. That's the way you move something out of a box. And when you do that, the box will free the heap memory that your T object used to occupy. But the T object itself is still valid. And you have it now, and you just have it by value in the normal Rust way, which basically means on the stack. Again, that stack heap distinction. So this moves out of the box and actually frees some memory. Box is pretty much the only type that does this. It's a little bit magic, but that works. And then we return, of course, we're returning option T, so we wrap it in a sum, make it an option. So that's pop. And that gets us pretty far. These functions work. It turns out there's one more detail that we need to worry about, and this will be the last detail in this video, and then we'll be done. But it turns out that this code handles memory correctly, right? So every box that we allocated in push, here is where we allocate the box, gets converted back into a box and then implicitly deallocated in pop if we pop the element. But it's also possible to just leave elements in the linked list, and then the linked list might go away. And we do need to make sure that the right thing happens there, because unfortunately, C does not know how to free our void stars. So we do want to worry about leaking memory in the list if there are still elements in the list when the list is dropped. So it turns out that the way we fix that looks like this. It's kind of shockingly short. So we're going to implement the drop trait. This is the standard Rust drop trait for our linked list. And when the linked list is dropped, while loop, with no body. So this is the condition of the while loop. So we loop over self pop is sum. So we keep calling self.pop. And as long as it keeps returning sum, we keep calling it. And then eventually self.pop returns none. And at that point, this while loop, the condition is false and it breaks the loop. And the drop returns. So every element that gets left in the list when the list is dropped needs to get popped out. And we can go back and remind ourselves, okay, so pop, it's going to from raw the element pointer that we get. And then that memory that was allocated here gets kind of implicitly freed here when we consume the box. Okay. And then the T got returned. In this case, all of these calls to pop that actually return an element will return some T. And if T was I32, then it doesn't matter because I32s don't need to free anything. They're just integers. They're just on the stack. But, if T was a string or a vec or a hash map or any other more complicated type, then that type that we return here would still own some stuff. It would have its own drop implementation. And then that return value of pop, we call a method on it, but then we don't save it. So that kind of automatically gets dropped the normal Rust way. It's what we call a temporary every time we do this. So it's going to get freed correctly. So this solves the memory leak, which is nice. I have one more command. It's nice to actually see that instead of just trusting that that's correct. So the last slide here is this funny command. So this is cargo test. You don't memorize this. You just Google it whenever you need to. But this is cargo test with the AddressSanitizer turned on. And you can see that I'm going to turn it on both the C side and the Rust side. And normally we use AddressSanitizer to make sure we haven't made any mistakes with dangling pointers. We're not accessing pointers that we've already freed. That's a mistake we can make in C. When we're calling C code, it's a pretty good idea to turn on the AddressSanitizer and check if we made those mistakes. In this case, I'm going to use it for another feature of AddressSanitizer. Is it also detects leaks. Actually, it will notice if we leaked any memory, which is very nice. So I'm going to run this. We need the nightly tool chain. I think the Z flags are unstable. So you just go find the slides or Google it whenever you want to do this. So I can go here and I can run it and it should pass. I expect this to pass. Yeah, it passed. But then we can go in and make it fail, right? So we can go in here, and again, this is libd.rs, and we saw this is where we included the stuff that Bindgen generated, and then we defined the linked list structure. There's new and push and pop. We saw all this code. And here's drop. So I'm just going to delete the drop impl. Okay. So if I delete the drop impl, go back to my terminal. So cargo test is going to pass, and we know. Actually, let's look at this test, right? So I have this test at the bottom, test drop, where I'm pushing 3 integers, 3 I32s, into a linked list. We kind of know that because I deleted the drop impl, those are getting leaked. So test drop isn't failing by default, but if we go back and run that more complicated command where AddressSanitizer turns on, what we'll see is that test drop appears to succeed, but then the whole test process fails when it tries to exit with this giant error that ASAN is turning on. And we can scroll up and we can see what ASAN is telling us. Yeah, with leak. So we've leaked 12 bytes, right? So each of these I32s is 4 bytes. We put 3 of them in the list and then we forgot about them. So without the drop impl popping those out, we've leaked all 3 of the, I think in this case, it's actually both the boxes and the malloc that we did in C. I think if we scroll up, we should see more leaks. Am I going to see 24? 32. I have to think about it. Sometimes it's hard to figure out exactly why you leak exactly the number that you do. But we've leaked the boxes from the Rust side and we've leaked the mallocs from the C side. It's both, in some combination. And so if we go back and we just put that drop implementation back in, save that, and rerun that test, we saw before that now it passes. And now we're actually freeing the memory. So AddressSanitizer can give us confidence that we got that right. So this has been a somewhat more complicated example of calling C functions from Rust. Remember, if there was any one thing that you memorize from this video, from this talk, memorize the CC crate. We saw it here in the linked list, and we saw it back here in the build.rs. The CC crate is amazing, especially for playing with this stuff. You know, if you have a project at work that already has a complex build system, make files or CMake or something, well, you might have to figure out how to invoke that. And that's going to be a little bit more complicated. But when you're playing with little hello world C files, you use the CC crate. It's very nice. Sometimes you can use it for more production use cases too. Yeah, so if you memorize one thing, memorize CC. If you memorize two things, memorize Bindgen. So Bindgen is how you consume big headers and generate the Rust bindings that let you call those functions. It's still unsafe to call them, right? So we still have to be careful, but at least hopefully it helps us get the types right. So this is a bunch of stuff. I think most of us will not memorize any of this. This is the sort of stuff that we Google when we need it. But hopefully this gives you some examples and some reference points, and you can come back later when you need it and copy paste and whatever you need to do. So that's foreign functions, calling C from Rust and Rust from C. Thanks for listening.